Over 53 years. That's how long humanity went without sending a single human being beyond low Earth orbit. In fact, the last time astronauts actually traveled to the moon, Richard Nixon was in the White House, the Beatles had just broken up, and your parents, or maybe even your grandparents, were watching it live on a grainy television screen. Then, on April 1st, 2026, the largest rocket that NASA had ever built lit the Florida sky on fire and changed that forever. Now, this is a really big deal, and not just for NASA, not just for the United States, but for all of humanity. Because this mission represents something rare in human history. It's when a species takes deliberate steps towards becoming a multiplanetary species. We are, after 5 decades of waiting, finally going back to the moon. And this time we're going back to stay. Now, I spent several years as a space shuttle flight controller in mission control, and I did work on Orion early on in its development, so I have a very small window into what this kind of mission demands from the thousands of people who make it possible. So this is a story about thousands of people coming together for the common goal of getting humanity back to the moon. But at its core, it's about 4 extraordinary human beings on the top of the rocket and the team behind them building an amazing machine with amazing engineering and a journey that covered nearly 700,000 miles of deep space. So today, I'd like to recap the Artemis II mission. I'd like to cover the crew that flew on the journey, the engineering of this ship, the flight plan, the activities, the mission objectives, and what actually happened on humanity's first trip back to the moon in over 53 years. First, let's meet the 4 people who made history with this mission. Reid Wiseman commanded the Artemis II mission. He's a 27-year Navy veteran and a former fighter pilot. Wiseman already lived aboard the International Space Station for 165 days, conducting numerous spacewalks. Victor Glover flew as pilot of this mission. He was a Navy test pilot with experience in the FA-18 Super Hornet, and he'd previously spent 6 months aboard the International Space Station. He's cool, he's precise, he's enormously skilled. Glover was the kind of pilot you want at the controls when things get complicated. Next up, we have Christina Koch. She served as the Mission Specialist. She holds the all-time record for the longest single spaceflight by a woman, 328 days aboard the ISS. She also stayed at the South Pole Research Station here on Earth in Antarctica for months at a time, over several years as a research scientist. And finally, last but not least, we have Jeremy Hansen. He rounded out the crew as the second mission specialist. He was a former Royal Canadian Air Force pilot, and with this mission, Hansen was the first Canadian to travel beyond low Earth orbit. Together, these 4 astronauts named their Orion spacecraft Integrity. That name would follow them for the entire 10-day journey to the moon and back. Now let's start at the beginning and talk about the flight hardware, the launch vehicle for this mission, the upper stage, and the craft that took them to the moon and got them home. Now, the rocket that actually carried them is called the Space Launch System, or SLS. It stands about 322 feet tall, about as tall as a 30-story building. And at liftoff, it generates a mind-boggling 8.8 million pounds of thrust. It's hard to fathom that that is 17% more thrust than the mighty Saturn V rocket that carried Apollo astronauts to the moon in the 1960s and the 1970s. Let that sink in. Now, the SLS rocket is built around 4 RS-25 engines at the base of the core stage. The core stage is that orange stage in the middle. These are not new engines. They're actually shuttle-era main engines that used to be at the bottom of the orbiter when we launched the space shuttle. They're deeply trusted after more than 135 shuttle missions, but they've been upgraded, running at higher thrust levels than they ever did on the space shuttle program. Together, at the bottom of the core stage, those 4 engines produce about 2 million pounds of thrust total. But the real muscle of the SLS at liftoff actually comes from the 2 massive white solid rocket boosters strapped to the sides. These are the largest solid rocket boosters ever built by a wide margin. Each one stands about 177 feet tall and burns through about 1.1 million pounds of solid fuel in just over 2 minutes, producing about 3.6 million pounds of thrust each. You put 2 of those guys together, it produces about 7.2 million pounds of thrust, roughly 75% of the vehicle's total liftoff thrust. Now, on the space shuttle stack, those side solid rocket boosters had 4 segments of propellant. They're stacked and connected together. On the SLS, those boosters now have 5 segments, giving them about 25% more fuel and more burn time for deeper space trajectories. Now, one significant difference from the shuttle is that the SLS boosters were not actually recovered. They separated over the Atlantic Ocean and splashed down, never to fly again. Now, sitting at the very top of the rocket above the core stage is called the Interim Cryogenic Propulsion Stage. That's the ICPS. That's an upper stage, and it runs on a single RL-10 engine burning liquid hydrogen and liquid oxygen, producing about 24,750 pounds of thrust. It's sized for the sole job of changing Orion's trajectory for the trip to the moon. Now, up on top of that upper stage, we have what we call the Orion spacecraft. Actually consists of the spacecraft where the crew is and the European service module actually connected together. Now we have the crew module, that's the pressurized volume where the 4 astronauts live and work. That's pressurized, has the heat shield for re-entry. That's connected to the service module that was built by Airbus and the European Space Agency. You can kind of think of the crew module as the cockpit and the cabin and the living space, with the heat shield for re-entry, that's critical obviously to get home. And we have the service module, you can think of that connected to it as sort of like the engine room. The crew module is 16.5 feet in diameter. That's about 20% larger than the old Apollo command module, which was built for 3 astronauts going to the moon. Orion fits 4 astronauts and has a digital glass cockpit of instruments with multiple screens and modern interfaces rather than the analog dials and switches of the Apollo program. And as you might guess, the computing systems in this thing are about 75% lighter and 20,000 times faster than Apollo's single flight computer. Now, Orion's avionics are designed with redundancy built throughout. And when I say avionics, I mean the flight computers, all of the boxes that sit between the flight computers and the thrusters and anything else that needs to happen like the solar arrays. All of that computer system is called avionics. Multiple redundant computers are constantly voting and cross-checking against each other in a distributed architecture. They're always looking for errors in computer outputs. Now, the crew module has 12 reaction control system thrusters for attitude adjustments and orientation during certain phases of flight. Those are the very small thrusters that are fired to point the spacecraft in different directions when you're in space. Now, the service module is critically important for the whole mission. It actually does the heavy lifting for everything else. It houses the spacecraft's main engine on the back for propulsion, which is a single hypergolic propellant engine. Now, hypergolic is cool all by itself. It means that the fuel and the oxidizer ignite on contact with each other, no spark, no flame needed for that engine to burn. This type of engine is super reliable. It was also used on the Space Shuttle program in orbit, and it fires for the critical trans-lunar injection burn and for other major maneuvers. The service module also has 8 auxiliary engines and 24 additional reaction control system thrusters for finer attitude control of the whole thing when it's connected together. Together, those thruster systems give the crew the ability to point the spacecraft in precisely any direction. Now, the service module generates electrical power through 4 large solar arrays. They call them solar array wings, SAW, as you might hear on the air-to-ground loops. Those deploy after reaching orbit. Those solar arrays altogether produce about 11 kilowatts of power. That's enough to run a small house. Now, there are also batteries on board for backup power and also for those periods when the solar arrays are either not deployed yet or not illuminated on the dark side of the Earth. Now, as you might guess, all of these electronics in the spacecraft, they generate heat, right? And the heat generated by electronics is actually rejected from the spacecraft through radiators on the service module. Because in the vacuum of space, there's no air around you to carry the heat away. Radiation is the only option. Now, when you think about it, everything in thermal motion has heat associated with it. My body has heat. But here on Earth, I'm surrounded by an atmosphere. If I jump in a swimming pool, I'm going to be surrounded by water. So if I'm a very hot piece of electronics, I can get rid of the heat, because you can't overheat your electronics. I can get rid of the heat through conduction or convection. Basically, matter is surrounding me, taking the heat away. But one of the biggest problems in spacecraft that most people don't really think about every day is that there's no air or very little air around you. So you can't, through conduction or convection, get rid of any of the heat. So in the space shuttle, for instance, there were radiators as well. Those large cargo doors that opened up had radiators on the inside that would reject the heat into space, but not through conduction or convection, literally through radiation into the blackness of space. And so Orion has similar radiating systems on the service module. If the radiators spring a leak, or if they stop working, or if you just have no radiators at all, what's going to happen is those electronics are going to heat up the spacecraft. The electronics will eventually fail, it will get too hot for the crew, and the whole mission will fail. Now, life support in the service module provides oxygen to the crew stored in pressurized tanks, along with nitrogen for cabin pressure balance and tanks of potable water. Now, as you might have guessed, the crew module has a toilet. It's a $30 million piece of engineering called the Universal Waste Management System. Remember that. We're going to talk about that a little bit later. It's a major upgrade from the Apollo astronauts who had no toilet at all, and they basically just used plastic bags. Now, the service module stays coupled or connected to the crew module for the entire outbound journey, for all the way through the lunar flyby and the return cruise all the way back home. Only in the final hour or so before re-entry does that service module actually separate and burn up in the atmosphere. At that point, Orion's heat shield, which is located on the bottom of the crew capsule, faces forward into the atmosphere to absorb the enormous heat of re-entry. Now, before I get to the flight plan itself, I want to pause for a minute and talk about the sheer scale of what we're talking about. Because every single illustration that you've ever seen of the Earth-Moon system essentially has lied to you. Now, this is not to scale, but if this were the Earth, every textbook diagram that you've probably ever seen has an Earth, around that size, let's say, and a moon, which is often, drawn different size than this. This is not to scale, but they're pretty much situated something like this, fairly close together. This picture in your mind of the moon being relatively close to the Earth is totally false. In reality, the moon is about 239,000 miles away from the Earth, about 384,000 kilometers. To put that into perspective, you could line up about 30 Earths side by side between here and the moon. I want you to take a minute to visualize that. 30 Earths. So here is the Earth, let's say, and here's the moon. This is not to scale, it's not the right size moon, right? One Earth diameter away from this would be about to here. That's one Earth diameter. Now imagine I cannot stretch my arms far enough out sideways. Imagine 30 Earths. There's one, there's two, there's three. Imagine 30 Earth diameters. That's how far away the moon is. So when you look at pictures of the Earth and the moon, and they appear to be this thing that you can just get to, imagine that Orion and the astronauts are going to be traveling an enormous distance. And by the same token, when we look at pictures from the lunar vicinity back over the shoulder of the moon and seeing the Earth in the distance, we're looking at an enormous distance of about 30 Earth diameters that exist between them. And so the bottom line is when you realize that the Earth is nearly 8,000 miles across, and you need 30 of them end to end just to reach our nearest neighbor. The scale of this mission is really incredible. The International Space Station, which all by itself is an amazing program and amazing engineering, but by comparison, the ISS only orbits above the Earth about 250 miles. Not 25,000 or 2,000, just 250 miles. It's barely a scratch off the surface of the Earth at this scale. These 4 astronauts for the Orion missions, they're out where almost no human has ever been. Now I'd like to share with you a big picture flight plan with the big events. Then we'll dive in and zoom in a little more detail as we go through it. So the mission launched on April 1st, 2026 and splashed down April 10th, a nearly 10-day round trip covering about 695,000 miles in total. So our big picture summary starts off with liftoff of the SLS stacked with Orion at the top. It boosted that payload into orbit in about 8 minutes. Orion, which remember has the crew on board, and the ICPS, that's the upper stage booster, it circled the Earth twice over about 23 hours while the crew checked out the spacecraft and stowed equipment in the cabin. The ICPS engine boosted Orion's orbit to about 43,000 miles in an elliptical orbit that's in preparation for actually going to the moon. Then the ICPS booster stage separated from everything else, and the service module connected to the command module, that's where the crew is actually living, performed the critical trans-lunar injection burn. We call that TLI. That burn was a critical burn in getting us to the moon. It's a 6-minute firing that broke Orion free of the Earth's gravity and sent them toward the moon. From there, it was roughly a 4-day cruise. Now, the lunar flyby itself happened on April 6th. Then they rode a free return trajectory home. We're going to talk about that in a lot more detail in a minute. And they arrived back at Earth on April 10th for a Pacific Ocean splashdown. Now that's the executive summary, the big picture, so to speak. Now what I'd like to do is dive in detail, go day by day, cover the mission beat by beat, so you can really understand the historical spaceflight milestone that was just executed. Here we are at launch day, April 1st, 6:35 p.m. Eastern Time, Launch Complex 39B at the Kennedy Space Center. It lit up. The RS-25 engines ignited about 7 seconds before liftoff. During this time, when those engines are burning, before the solid rocket boosters ignite on the sides, the onboard computers are actually verifying the health of all 4 engines before committing to launch. And what happens is, if the engines are all healthy, the computers command the firing of the solid rocket boosters and the system lifts off the launch pad. Now, if you notice, there is a large amount of water being dumped on the launch pad directly under those engines right before liftoff. Most people that think that water is down there to somehow put out a fire or make sure a fire doesn't spread or something. Actually, in the early days of spaceflight, when they didn't throw water on the launch pad, the intense sound pressure from all of the engines firing actually reflected off the concrete and potentially damaged some of the engines in the early part of spaceflight. So they installed this water deluge system, dumping tons and tons of water, literally, onto the launch pad. The main reason it's there is to absorb the acoustical energy and absorb it into the water so it doesn't reflect back up to the spacecraft and damage the engines when it's just a little bit above the ground. Now you might wonder what would happen if these engines, the core engines, are commanded to fire, but there's a problem detected before the solid rocket boosters ignite. Well, the computers are verifying the health, the throttle settings, the temperatures, the pressures, all of the internal instrumentation. If anything is detected to be out of spec in that window before the solid rocket boosters ignite, then the computers command a shutdown and we abort right on the launch pad. And so what happens is, during those 7 seconds, the computer's checking to make sure all systems are go, and if they are, they command the firing. So once the flight computers confirm full engine power during that window, the solid rocket boosters are ignited at T0. And here's a detail worth knowing. Once these boosters light, there's no stopping them, and I mean that quite literally. Solid rocket motors cannot be throttled or shut off once they are lit. Once they fire, as we said at NASA, you're definitely going to go somewhere. So liquid-fueled engines, like the core stage engines, you can throttle them by controlling the amount of fuel and oxidizer injected into the combustion chamber. You can't do that with a solid rocket booster. There's no liquid in there. It's literally a hardened solid powder that's burning from the inside out. Now, actually, the solid rocket boosters do throttle a little bit because as you go through the atmosphere, they do have a throttle profile, but it's not done by, injecting liquids or anything. The way the casings are made on the inside, there is a pattern that they're actually basically hardened into the inside of those solid rocket boosters. And as the rocket burns from the inside out, the surface area changes on the inside, and so there's a built-in throttle profile. But the crew cannot press a button to shut that engine down, and they can't throttle it back or throttle it up in real time. And so when those rockets ignite, you're definitely going to leave the launch pad. Now, as I said before, this vehicle produced a mind-boggling 8.8 million pounds of thrust and began rising during liftoff. For the first 2 minutes, the ride was powerful. Astronauts typically experience about 1 to 2 Gs, maybe a little bit above that, during this phase of flight. Now here is a crazy awesome comparison between the SLS launching side by side with the mighty Saturn V, which had no solid rocket motors. It was all liquid boosters, side by side, and you can see the difference at which these two rockets leave the launch pad. Now, at about 2 minutes into flight, having reached roughly 30 miles of altitude and traveling around 3,100 miles per hour, the boosters separate. Those solid rocket motors, they separate and they tumble away into the Atlantic Ocean. Once the SRBs separate, the vehicle gets noticeably smoother and quieter because the solid boosters are the major source of vibration and sound. Now, at the top of the Orion capsule, just above that, is actually called the Launch Abort System. It's called the LAS for short, and it's sitting there ready to pull the crew capsule away with its own set of rocket motors if there's any kind of explosion or other problem down below. So for a good chunk of the launch profile, the astronauts can be pulled away, and that system was tested extensively during development of this program. But after we get past the regime when you can feasibly pull the crew away, we need to get rid of this abort tower, this launch abort system. So at this point in the flight profile, the launch abort system gets jettisoned. It gets pulled away and tractored away from the rocket, revealing the windows of the Orion, and so that the launch abort tower is no longer present anymore. Now, once the solid rocket boosters are separated, the 4 RS-25 engines at the bottom, they continue burning for the remaining 6 minutes of ascent, completing the 8-minute push to orbit. At engine shutdown, the crew was now in space. Now, right after reaching orbit, it is a very, very busy time. The crew has a lot to do. Orion's 4 solar array wings, they have to be unfolded and begin to generate electrical power. The crew transitioned from their bulky launch and entry suits, the pressure suits, to more comfortable flight suits. They stow gear, they fold things up, they clear the cabin. They begin working through a long checklist of onboard system verifications. You want to make sure the spacecraft is operating exactly as you expect, because if it's not, you don't want to be on your way to the moon. You want to execute an abort and come back to Earth. Now, one of the first challenges in space, actually, for astronauts is space motion sickness. It's a real thing. Even experienced astronauts, fighter pilots who've done all kinds of things in the air, they can often feel disoriented as the vestibular system inside your inner ear tries to make sense of weightlessness. So in the middle of checklists and stowing and getting ready, very often astronauts can feel sick to their stomach in space. So in the first 24 hours after getting to orbit, the crew executes checkout after checkout of onboard systems. Think electrical systems, think thermal systems to reject the heat, think propulsion, think avionics, anything computer related or commander related, and more, configuring Orion for the outbound journey to the moon. And yes, you may have heard that the toilet broke, or at least didn't work exactly as planned on this mission, almost immediately after they got into orbit. First, the pump in that system wasn't quite primed with enough water, which was a very, very easy fix. And then, partway through flight day 3, the vent line for the liquid waste actually froze, probably due to a combination of cold temperatures and some sort of chemical interaction in the waste system. That's the thing with space. If you're facing the sun, the surface of the ship can get hot. As soon as you face away, it can get really, really cold. So flight controllers turn the spacecraft to actually face the sun to warm that frozen line for the waste management system. Eventually, it thawed out and it resumed working, though the crew dealt with intermittent toilet issues for much of the rest of the mission. Now, it might seem funny to joke about the toilet. You know, they could get all the way to the moon, the toilet didn't work. But remember that we test almost everything on Earth, but weightlessness testing is not possible on Earth. There is no anti-gravity chamber here. The closest we can get is flying a parabolic arc in an aircraft doing some sort of free fall. So some things, because of the weightlessness and the temperature gradients, they really have to be tested by flying them in space and learning how they work and how they interact and refining the design over time. Now here we get to the trans-lunar injection. On the evening of flight day 2, the engine fired for around 6 minutes. This was, as I just said, the trans-lunar injection burn. We call it TLI. So on the air-to-ground loops, you hear TLI, TLI. They're talking about the burn that sends you to the moon. It's one of the most important moments of the entire mission. Now, here's what makes TLI so critical and a little bit scary. The crew was actually not aiming for where the moon was, like as if they were looking at it out the window. They were actually aiming, the ship thrusters, for where the moon would actually be in the future, 4 days later, when Orion arrived at that point in space. It's kind of like throwing a football not to where the receiver actually is at that moment in time, but to where that person will be running to in the future. The moon is roughly moving in its orbit about 2,300 miles per hour, and mission planners had to calculate precisely where the path would be when Orion arrived to target the burn correctly. Obviously, I've never been in space, but I think it'd be pretty wild to be here in Earth orbit. You have the moon, again, 38 Earth diameters that way, but I'm putting it here so you can see it, right? And you point your spacecraft and you execute this TLI burn, right? But you're not aiming for the moon. You're not looking at the moon directly. Like if you're over here, you're not looking at the moon. The moon is going around the Earth, right? And so you're aiming to where the moon will be. So you're aiming to empty space over here. And you just have to trust that they've done the math correctly and that they've double-checked their work, because in some crazy scenario, if they target the burn incorrectly, where you don't intercept the moon 4 days in the future, then you just sail out and basically are lost in space. So after the TLI burn, Orion was traveling roughly at 24,500 miles per hour. 24,500 miles an hour. I want you to remember this speed because Orion will again be traveling at this speed roughly when it returns home for re-entry, and I'll talk about why in a few minutes. From this point forward, after TLI was executed, something profound began to happen. The Earth started to get smaller out the window. Think about it. You're looking out the window, and over time, you look back and the Earth is smaller and smaller every time you look.
And that is the beautiful Earth in the window.
So on the International Space Station, much lower orbit, astronauts orbit about 250 miles above the Earth, always close to the Earth. They can always see the continents. They can see the coastlines. They can see the oceans all the time. But now, for the first time in more than 50 years, human beings were watching the Earth shrink in their windows. Astronaut Christina Koch photographed Earth from Orion's windows, and the images came back were extraordinary. Earth appeared as a brilliant blue and white crescent, suspended in a totally inky, absolute black darkness. The camera sensitivity was cranked up very high to capture the dark side of the planet, the nighttime side of the planet, right? And you could actually see the aurora on the Earth glowing near the top of the globe there. The swirling atmosphere, the curvature of the Earth, all to plainly see. These were views that only 24 human beings, the Apollo astronauts, had ever seen before. Aboard Orion, daily life was a mix of serious work and small human moments. The crew exercised on a flywheel device to prevent muscle atrophy and stay strong for the journey. They go about their daily life. They exercise. They go to the restroom. They ate space food, which are meals that are either freeze-dried or rehydrated with water from a dispenser, or packaged in a thermostabilized form, ready to eat. So what did they eat? Well, things like mac and cheese, shrimp cocktail, chocolate pudding, and tortillas. Actually, fun fact, tortillas are a staple in spaceflight because, unlike bread, which can get crumbly and float everywhere, tortillas don't produce very many crumbs that float around the cabin and get into equipment. Drinks are rehydrated from powder. Nothing floats away freely. Everything has to be secured or eaten immediately.
The end of a long day. Listening to our Artemis II playlist. Making some dinner.
And of course, as they're eating and drinking and conversing, they looked out the windows constantly. Wiseman later joked that the windows got dirty because the crew was pressing against them so much with their faces. In the pure vacuum of deep space, stars don't twinkle. They don't shimmer like they do here on Earth. They are hard, fixed points of bright light because there's no atmosphere when you're way out there. More stars than you've ever seen in your life, blazing against a blackness that has no analogy or no analog on Earth. And when something simple like the toilet venting the liquid waste overboard, something remarkable happened that Christina Koch showed on her camera. The waste actually trickled out into space as a glowing, gem-like set of crystals spraying and sparkling past the windows before disappearing. Obviously, inside the ship, the liquid waste is liquid, but in the vacuum of space, liquids instantly freeze into tiny, tiny ice crystals. It was simultaneously kind of hilarious and beautiful. The moon gets closer and closer, and as the days passed on, the moon grew and grew in appearance through the windows. The moon is a world with no atmosphere, no weather, no softening of its features. Every crater, every ridge, every shadow appear crisp and ancient to the crew. The crew was approaching the moon on what we call a free return trajectory, and it's time to now talk about what that actually is. A free return trajectory is a path through space calculated so that if your engine fails entirely and you just can't turn your engine on anymore at all, if you can't fire it, if it's totally inoperative, gravity alone will swing you around the moon and back to the Earth. So remember, the moon is somewhere over here, it's moving, the crew fires their TLI burn, and they're aiming for an empty point in space. The moon catches up to where they are, and the trajectory is calculated so that the moon's gravity bends the trajectory around the moon and then sends them flying back to the Earth, kind of like a slingshot. And all of that is done without firing the rocket engine. It's a very safe trajectory, guaranteeing that you make it back home. So you can kind of think of it as a built-in safety feature of the mission. Apollo 13 famously survived using a similar principle in 1970 after its oxygen tank exploded and they got that crew home. Because remember, on Apollo 13, they didn't know if they could even ignite the engine. They were actually worried if they ignited the engine that because of the previous explosion, the engine was damaged, that the entire ship might explode. Maybe the propellant lines were damaged. The engine just might explode. So they executed a free return trajectory to get them back home to Earth. So Artemis II flew a similar type of free return trajectory, meaning that even if the service module engine died or failed or didn't work, the crew would come home. That's good engineering philosophy. What you do is you design your rescue path into the trajectory itself. Now, as the crew approaches the moon, I want to talk about the communications blackout that they had. As the Orion curved around the moon, right, on its free return trajectory, the crew experienced something no human had encountered in over 50 years. The spacecraft passed behind the moon and all communication with Earth was shut off. And I don't mean that they shut it off. I don't mean that it was degraded. I just mean that it was completely gone. Radio waves obviously cannot travel through the moon to get to the Earth. So when they're on the back side of the moon, the entire moon is in the way, on the way to Earth, and there's no satellite constellation of communication satellites there. So for about 40 minutes, think about that, Mission Control had no contact with the crew whatsoever. That is among one of the longest communication blackouts in all of human spaceflight history. And having been in Mission Control myself, when we have LOS periods, loss of signal like that, you know, on the shuttle, LOS might be 5 minutes or maybe 8 minutes because we're handing off between satellites. So we never had a 40-minute blackout period, certainly with the crew that far away. Basically, if there's a cabin leak, or if there is a propulsion leak, or if there is a power failure, or if the computers fail, or whatever, during that period of time, well, actually during any phase of flight, the crew is trained to deal with the immediate safing of the system right then and there. Mission Control is there to help them with more detailed plans, more creative plans that maybe they don't have the ability to think of on the fly up there. Longer term planning, and also we're telling them the immediate steps to safe the system as well. But in that blackout period, I guarantee you there are procedures on board for every one of those systems failures to safe the system and put them in a safe configuration. So when they pop out the other side and we regain signal with them, then we can execute the plan, to get the crew home if something really bad happened. And so I'd venture to guess that one of the main objectives as soon as we get the moon base built in the future is to build a satellite constellation around the moon so that we're not in these LOS periods, or these loss of signal periods, with spacecraft that are orbiting above. So during that silent period, imagine 40 minutes of total solitude disconnected from the Earth. The crew witnessed an Earth set, the Earth dropping below the lunar horizon, followed by, eventually on the other side, an Earth rise as they emerged from the far side.
Would you look at that, man?
Wow, once the shadow's behind it, it's different.
Wow.
Along Earth.
Dude. No way. Fiend.
It's gone. It's gone. Oh my God.
Imagine being totally isolated and cut off communication-wise from every other human currently alive. You're with 3 of your buddies, 4 people total on the ship, and you're just taking in this moment, totally isolated from every other human currently alive. That moment of Earth set and Earth rise, echoing the iconic photograph taken by Apollo 8 astronauts in 1968, was witnessed live for this crew by the first time in more than half a century. And something else happened really interesting during that blackout period that stunned everyone: a total solar eclipse. You see, from Orion's position near the moon moved directly between the spacecraft and the sun, blocking the sun completely. And during the eclipse, they could still see the solar corona glowing around. You see, the corona of the sun is the outermost atmosphere of the sun. It's normally invisible from Earth. The crew described it as ethereal, as if the entire energy source of the solar system, everything that powers all photosynthesis and indirectly powers all of our civilization, had simply been switched off and replaced by a glowing ring of fire. And you might say, well, wait a minute, the sun doesn't power everything on Earth. He just lied to me. Well, I tell you what, let's do a quick thought experiment. Let's extinguish the sun. What's going to happen? Within a week, all plants are going to die. That's going to basically disrupt the food chain. Animals are not going to be able to eat. Humans will not be able to eat. Sure, we can still have coal reserves and some electricity for a while. We still have nuclear power plants. We'll still have electricity for a while. But ultimately, the energy of this planet, what we consider actual civilization, comes from the sun. You know, the weather systems, the wind moving around, all of our food coming from plants through the food chain. It's all really coming from the sun. You extinguish the sun, all of that stops. So if you're an astronaut and you're literally able to blot out the sun from the moon, totally disconnected from everyone on Earth, that must have been a mind-blowing experience. The images they captured were unlike anything previously photographed from a human spacecraft. Now, here's a common misconception. I want to talk about this because you hear this a lot. There is no permanent dark side of the moon. Even though personally I love Dark Side of the Moon and the music there, there is no dark side of the moon. The moon is tidally locked. meaning that the same face of the moon always points toward the Earth. But the other side of the moon, the dark side, so to speak, is not really dark. It gets sunlight regularly as the moon orbits. All right, I want to demo this real quick for you here. Pretend this is the moon. I'm choosing red so you can see the white bits here. It's going to be important in just a second. So we have the Earth, moon. Of course, it's actually 30 Earth diameters away, but I have to hold it close so you can see it. All right, now what you might think is happening is that the moon is going around, and notice the orientation doesn't change. You might think that the moon is going around the Earth in the same orientation. If that were the case, then everybody on Earth would eventually see all sides of the moon, because as the moon goes around, it would present different, basically like these people would see this side, and then these people over here would see the other side of the moon. But actually the moon is called tidal locking, or tidally locked. And it's not unusual. It's not like some mystical thing that the moon does, our moon. In fact, a lot of moons in the solar system are tidally locked to their planets. It has to do with the gravitational interactions over billions of years. It ends up setting up a resonant system like this. So the Earth, as you know, rotates, right? Well, the moon actually rotates, believe it or not. But the way that it mathematically falls out is basically as the moon goes around, the rotation of the moon eventually becomes locked to the period of its orbit. So instead of going in the same orientation, like I'm doing right here in front of you, the moon is rotating. It's rotating, but it's also going around the Earth as it rotates at the same angular rate. So focus your attention on this little peg sticking out here. So it's going and so it's rotating, and as it's orbiting, but it's rotating as it's orbiting. So this peg always faces the ground. And so even over here on the other side of the planet, the same peg is facing. So that's why when we look up in the night sky, the moon is rotating and it's orbiting, but they're tidally locked. So the rotation rate and the orbit rate are the same. So we always see the same side of the moon. But the Orion astronauts and the Apollo astronauts before, they are the few humans in history to see with their own eyes the other side of the moon. Now, because the other side of the moon is just, there's nothing special about it, it's over here. The sun, which you might think of my studio lights off in the distance, of course, are illuminating the other side of the moon. So Dark Side of the Moon is an awesome album. I love it. But there is no dark side of the moon. The thing is rotating and all sides are getting illuminated as the moon orbits the Earth. So instead of the dark side of the moon, it's actually more accurate to call it the far side of the moon, the side that we don't see. The Artemis II crew saw portions of the far side of the moon that no human eyes had ever directly observed, including the first direct human view of the Oriental Basin, a massive impact structure on the far side of the moon, nearly 600 miles across. Now, the crew passed within about 4,070 miles of the lunar surface at its closest approach. It wasn't going in an orbit around the moon, it was flying behind the moon in a flyby on that free return trajectory to come home. But at that distance, just over 4,000 miles, it's close enough to see incredible detail. With their naked eyes, they could clearly see craters. They could see ridges on the surface of the moon. They could see shadows stretching across crater rims, and the stark contrast between the highlands of the moon and the basins. And with the zoom lenses, which were attached to their cameras, they captured close-up images of individual craters with enough resolution to see their internal structure. Now, there were cameras on the Orion solar array wings outside the spaceship as well, and they also broadcast live views of the lunar surface to the Earth. Now, at this point in the mission, the crew actually set a new human distance record, the farthest any humans had ever been, 252,756 miles from Earth, breaking the previous record set by Apollo 13 in 1970 by about 4,100 miles. So this crew literally has traveled farther than any other humans ever. And then came the moment that brought the world to tears, and I do mean literally. As they observed the far side of the moon, the crew identified two small unnamed craters. Now, they had the naming rights as they were the first humans to ever directly observe them. Mission Specialist Hansen, his voice audibly shaking, radioed Mission Control.
And especially meaningful for this crew is a number of years ago we started this journey in our close-knit astronaut family, and we lost a loved one. And there's a feature in a really neat place on the moon, and it is on the near side, far side boundary. In fact, it's just on the near side of that boundary, and so at certain times of the moon's transit around Earth, we will be able to see this from Earth. And so we lost a loved one. Her name was Carol, the spouse of Reid, the mother of Katie and Ellie. And if you want to find this one, you look at Glushko, and it's just to the northwest of that, at the same latitude as Ohm, and it's a bright spot on the moon. And we would like to call it Carol.
Now we get to talk about the journey home. After the lunar flyby, Orion was already on this free return trajectory. Gravity at this point was doing the work. No rocket engine boosting them home. Literally, gravity was pulling the spacecraft back towards the Earth. The cruise home took around 4 days. Earth grew larger and larger in the windows, reverse of getting smaller as it was before, the same brilliant blue marble getting closer and closer and more familiar. During this time, the crew performed final equipment stowage, suit checks, and systems verifications before re-entry. One of the most important pre-entry tests is actually called an RCS hot fire. That's a thruster hot firing. It's a brief test firing of the reaction control system thrusters to confirm and to make sure that they're functioning perfectly before the crew needs them to orient the heat shield for re-entry.
This is so freaking cool. Cool of your face too. That was awesome.
Temps look good, everything looks good, pressure looks good.
Remember, when they separate and start to come in, there's no air up there. There's no wings. They have to use the thrusters to orient the heat shield down. Otherwise, they cannot enter the atmosphere in a safe way. You can think of it as a final systems check on the most important piece of hardware standing between the crew and the atmosphere. The most important, except for, obviously, the heat shield and the parachute system. Here we get to re-entry, often called the most dangerous 13 minutes in the mission. At about 42 minutes before splashdown, just 42 minutes, the service module was jettisoned. It separates and it goes in a different direction from the spacecraft. It actually burns up harmlessly in the atmosphere. The crew was now flying solo in the crew capsule, and the heat shield was on the bottom of Orion. It was its only protection from the incredible energy of entry. At 7:53 Eastern Time on April 10th, Orion hit the upper atmosphere at a crazy altitude of 400,000 feet, roughly 75 miles up in the atmosphere. Right, that's entry interface, traveling at about 24,000 miles per hour. That is about 35 times faster than the speed of sound. So 24,000 miles an hour is an insane speed. Now for comparison, the space shuttle, which flew many, many times, re-entered the atmosphere at a cool 17,000 miles per hour from low Earth orbit. Going to the moon requires far more energy than going into low Earth orbit, and all of that energy has to come out in the form of heat. Now people often ask, well, why did they come back so fast? Why can't they just slow down? Well, when you think about it, remember that beautiful launch that we just watched a minute ago, right? All of that energy and all of the side boosters and the central engines, that was required to get that thing with that mass up into space. And then we did a TLI burn that boosted them all the way on a flyby around the moon. If you think about it, it's the same thing happening to this little red ball here from my chemistry kit. If I throw it up, it comes right back down in my hand. So when I throw it up, I give it energy. That's like launch. It's like launching the booster. But as it gets to the apex, it stops. Why? Because gravity has slowed it down. So I've turned the kinetic energy into potential energy, right? And then it starts to come back to Earth. It starts to fall down. That potential energy gets converted back to kinetic energy. If I had a little meter and I knew the speed, the exact speed that it left my hand, then that speed would bleed to zero. But when it came back down, it would be traveling at exactly the same speed that it left my hand, ignoring air resistance, okay, if I didn't have any air. All of the energy would go to zero into potential energy, and then it would all go back into kinetic energy, same speed going up as coming down, hitting my hand. That's called conservation of energy. And the same thing was happening to the Orion spacecraft. So you can pretend this is the Orion spacecraft, and it boosts its way off the Earth, and it gets over here, and then it have the ICPS burn, which raises it into an elliptical orbit, and then the TLI burn, which boosts it 30 Earth diameters that way. That's like throwing this thing up, up, up in the air. And eventually it gets there and it slows down and it turns around. So the orbital velocity, we said earlier before we made it all the way to the moon, was about 24,000 miles an hour. And so as it goes back and comes the other way, it slows down, and then as it accelerates home, the entire time the Earth is getting bigger and bigger in the window, it's accelerating. It's literally falling down from the moon. That's why it's going so fast. We boost it with all that energy to get there. And then as it slows down and barely turns around the moon and comes home, it's accelerating, literally falling from the moon. And the speed that it hits that atmosphere is the same speed that it had when it first left for the moon, about 24,000 miles an hour. And that's the speed that we need to get a payload with all the equipment to the moon, 250,000 miles away. Now the physics here is extreme. As Orion punched into the upper atmosphere, the molecules of air in the atmosphere physically could not get out of the way fast enough because it's coming in so fast. They compressed, major compression in front of that heat shield, and they ionized, forming a sheath around the spacecraft. That sheath is a superheated plasma that reaches about 5,000 degrees Fahrenheit, and the heat shield on the bottom of Orion's spacecraft is really what is keeping the crew protected. This is nearly as hot as the surface of the sun. The ablative heat shield is actually a material called avcoat. It doesn't just block this heat like some kind of Star Trek shield or anything. It absorbs it, and it actually burns away, carrying the heat away in a controlled process to take the thermal energy away from the capsule. When you think about it, all of the energy of launch, all of the booster fire and all that stuff that we saw, that energy was stored in potential energy when we got to the moon, and then it gets back to kinetic energy when we get back to Earth. So all of the energy of the explosions of launch, that has to be absorbed and dissipated by that heat shield. That is why entry is so incredibly important and something that we have to make sure is safe for the astronauts. And that's why it's also so hard to make a heat shield to protect them. Now, the space shuttle also reached thousands of degrees on re-entry, but much lower temperatures. So a lot of people say, well, why didn't we just use the exact same heat shield that the space shuttle used? Well, it's not sufficient. The energy coming back from the moon is way higher than any spacecraft coming in from low Earth orbit. So the heat shield is specially designed for these lunar trajectories. Now, this plasma sheath around it means the electrons are literally ripped off of the molecules in the atmosphere of the atoms. And that plasma also blocks radio signals. For 6 entire minutes, the crew was completely cut off from mission control, completely alone with only the heat shield between them and the equivalent of a small sun. When radio contact was restored, mission control exhaled, so to speak, as the peak heating was now over. Now, about 25,000 feet of altitude, 2 drogue parachutes, each about 23 feet in diameter, deployed, and they snapped open, stabilizing the capsule. Then, at about 6,000 feet, 3 enormous main parachutes, each 116 feet in diameter, covering more than 10,500 square feet of nylon, blossomed open, slowing the craft. Together, this system slowed down Orion from hundreds of miles an hour to about 17 to 19 miles an hour at water impact. There were backup chutes available if the primary chutes failed. So at 8:07 p.m. Eastern Time on April 10th, 2026, Orion splashed down into the Pacific Ocean southwest of San Diego. The crew was finally home after a 10-day journey, literally to the moon and back. Immediately, Navy divers reached the capsule. They deployed an inflatable raft called the front porch directly outside of the hatch on the exterior of the Orion capsule. They unbolted it and they opened the hatch. They climbed inside to assist the crew.
Yes! Do it. Sing it. Yes! Let's go! Pin.
Get your sail cover.
Sail cover.
Here. Right there. Got
We got you. I got you. I got you, laddie. So lean over. Take your time. Seal cover's on. All right, get it. All right. 4 green. Ike, welcome home. Christina, welcome home. Yes. Jeremy, absolutely welcome home, brother. There it is, Reid. What's up? Welcome home, brother. Thank you.
The astronauts stepped out one by one, getting their first feel of gravity again after 10 days of weightlessness. Remember, they're doing all of this in the middle of the ocean. Each astronaut was then hoisted into a waiting helicopter and then flown to a nearby ship. And after medical evaluations, they were then flown to shore and then to Houston. Now, after the crew was extracted, Orion itself, which again was still floating, they have airbags inflated with helium to keep it upright, was towed to a Navy ship well deck, the ship's interior dock. A crane on the ship then hoisted the capsule aboard, securing it for journey back to a naval base in San Diego and then later to the Kennedy Space Center, where engineers would begin painstaking post-flight analysis. I'd like to touch on what I like to call the invisible army here. You see, when you're watching Artemis II on a television screen, it can look almost easy. You launch a spaceship, you cruise to the moon, you fly by a moon, and you come home. But behind every single second of that mission, there were over 10,000 people across NASA, across contractors like Lockheed Martin, Northrop Grumman, Airbus, and dozens of other organizations who had spent years preparing for this. It looks so smooth and well executed because every failure that you never saw was one that someone had already simulated and practiced and survived in a windowless control room somewhere. Teams in mission control run hundreds of what we call integrated simulations before a flight. They simulate the entire flight, from launch, entry, landing, all of it, along with electrical failures, along with cabin leaks, along with computer crashes, coolant system anomalies and leaks, engine failures, abort scenarios, and anything else that you can possibly think of. It's been thought of and simulated ahead of time. And during those training simulations, the training team is deliberately throwing problems at the crew and at the flight control team. We're practicing at the same time in the same simulation simultaneously. You don't really discover your backup plan when things go wrong in the real space flight, at least if you can help it. You usually discover your backup plan months before launch, when a sim instructor injects a failure at the worst possible moment. And if we determine that we don't have a procedure for that, I guarantee you someone writes a procedure for that, so we have it in the books for the mission. Basically, the team practices until any failure has a response, until no alarm actually surprises you, until the training is so deep it becomes almost like a reflex. That is actually what makes spaceflight look so effortless and so smooth, doing things like going to the moon or building the ISS. It's the result of thousands of people practicing until they simply cannot get it wrong. I'd like to wrap it up by saying Artemis II was not the end of a journey. In fact, it was simply the first act of our return to the moon. Future Artemis missions will perform a similar launch but do different things on the trip. They will perform evaluation and checkout of new lunar landers to go down to the moon. We'll test those in space in lunar orbit. And then we will land humans on the lunar South Pole for the first time in history. Now, the South Pole of the moon is actually really interesting to go back to because it's a region believed to hold water ice, actual water frozen in permanently shadowed craters at that region of the moon, which changes everything about what's possible on the moon. Basically, if we can get to the water that's frozen on the moon, it could allow us to live off the land, so to speak, and use the water that's already on the moon, from everything from drinking to making rocket fuel. So follow-on missions in the Artemis program will build infrastructure. They will build habitats. They will build power systems. They will build rovers. They'll eventually build a permanent lunar base, much like the ISS, but on the moon, where humans will live and work in a world that is not Earth. The Artemis program's stated goal is not just to visit the moon, but to stay on the moon. We don't want to go, plant a flag and come home. We want to live and work there. And so the interesting thing is that children born today will grow up in a world where human beings live on other planets. Think about those words. This is not science fiction. It's the trajectory we are on, and Artemis II was the first moment and the first footstep that was taken. Humanity has always defined itself by the horizon. What is next? What lies beyond the next range of mountains? What is over there? What's beyond the next ocean? What does the sky above some distant land look like? This mission, Artemis II, is the start of something irreversible. We have chosen, once again, to go out there. Learn anything at mathandscience.com.